All right, so today we're going to talk about trigonometric substitution. And this is going to work when you have, it doesn't have to be x, could be a function of x. But whenever you have something that depends on x squared, let's just say x right now, x squared minus a squared. So they're going to be things of the form x squared minus uh, a squared minus x squared, and a squared plus x squared. And this it should give you, so there's three different cases, and they should give you an idea that there should be a triangle somewhere here. So why? Well, let's do each one of them. Let's write them here and let's try to look at what is the triangle that corresponds. He'll be like, I don't see any triangles at all. So a squared plus x squared, a squared minus x squared, and x squared minus a squared. So those are going to be our three cases we're going to explore. So let's throw in some lines and let's take a look at what happens. Each one of them will correspond to a triangle. Why? Well, this is the easiest one to see. Because if I just set it equal to c squared, then what that will correspond to is a right triangle where my sides c squared will correspond to this. Oh, sorry, just c is the hypotenuse. And this will correspond to x, and this will correspond to a. And this is a right triangle, of course. You see, this right here gives you the inkling that there's a Pythagorean theorem going around what you have here. So that, if you use that triangle, let's read what we can get from that triangle. We get that x divided by a is opposite over adjacent. That's going to be the tangent of that angle. From there, I'm going to, well, that was a little loud. From that, I'm going to multiply times a on both sides. Apparently I got very excited about it. Then I can take my derivative. So that's going to be the substitution I'm going to be using. And I get dx is going to be a secant squared of the angle d theta. Now, we can read this information right off of our triangle. But if you go ahead and take a square root on both sides here, c is the side of a triangle, so it's positive. And you just get, this is the square root of a squared plus x squared. And from that, you can, oh, I realized I was so low in the page. Well, it's okay. C divided by A is, what is C divided by A? Is hypotenuse over adjacent. Now, remember what is adjacent over hypotenuse is the cosine. But hypotenuse over adjacent is the reciprocal of it. You're just flipping the fraction. So if you flip that fraction, then hypotenuse over adjacent is the secant, which is the reciprocal of the cosine. So I'm going to write the secant here because I'm going to have to multiply both sides times a because I'm going to have issues. So c over a is going to be square root of a squared plus x squared. And then divided by a, but I'm going to multiply it on this other side. Usually this is the term you want to integrate or a power of it. So by using this triangle, then you can just substitute it in with a secant of the angle. Okay, so you don't have to, what happens, other people go ahead and just substitute in x everywhere and substitute dx, and they end up with a lot of trigonometric identities to deal with, and I find that people have issues with those identities. I think it's easier to do your SOHCAHTOA, as much as I hate that, but you know, it's probably easier. Let's go ahead and address this, the first integral that we had, or the integral with that form, where in this case, so putting everything together that we had there. So let me go ahead and pause the video. I'm going to move everything to give myself room. Okay, so we're in this situation, right? So as I told you, a in this case is 1. X, I told you our substitution would be a times the tangent, but a is 1. So it'll just be the tangent. And let me scroll so we can actually try to see everything we have here. So x is a times the tangent, so just 1. Dx, we computed it, is just going to be our secant squared. And this just becomes 1 over 1 plus, oh, my bad. Well, that's not the way you do it. As I told you, I mean, you could. Okay, take it back. Let me write it out. You could. It's just not as nice. I'm just substituting the x with the tangent, and then instead of the secant, I'm going to put a, instead of, sorry, the dx, I'm going to write a secant squared. So doing my highlighter, this right here would be my dx, and this may be a little too dark. This one right here is just, I'm substituting in actually just the tangent right there. That's the x squared I have there, and then the dx was the other one I had there. All right, so that's one way of doing it, and of course, the only thing you'd have to remember is that 1 plus tangent squared is secant squared, and then this would just become secant squared over secant to the 4th by substituting in. Let's do square square, just because. And that would give us the integral of one of the squares cancel, and you get 1 over the secant squared, and you remember that the secant squared is nothing but the reciprocal of the cosine, and this becomes the integral of the cosine square of theta, for which you can do your 1 plus cosine of 2 theta over theta. And you can go ahead, oh sorry, theta over 2, goodness, that came out of left field. You can now integrate here, and the one thing you will need to have is your, once you want to take back your substitution, is the identities for the cosine of 2 theta, because, or the sine of 2 theta, because when you integrate, you're going to get a sine of 2 theta coming out of that. I'll remind you, sine of 2 theta is 2 sine of theta cosine theta, but you can integrate this now using our all the techniques we used in the previous section. So let's examine the next case. So the next one is 9 is the form a squared minus x squared. Let's go to our triangle a squared minus x squared, and let's draw the triangle here. So now, how do I do that? Well, I notice that, well, I have a minus. What that means is if I would just set something, let's say equals to b squared, if you will, then what I know is that the first guy is the big guy, because you have a minus. So let me go ahead and add on both sides just so you see what I'm talking about. If I add x squared on both sides, just saying the big guy doesn't really help a lot. But you see a squared is the hypotenuse because that's the guy who is written as the sum of the other two. So a must go here. Whenever you have a minus, the first term is going to be your hypotenuse. So let's extrapolate to that to the next case. So if we have that being our triangle, then by what we just discussed, this has to be the x, because that, in that case, we have that the first guy, the big guy, is the hypotenuse. Okay, so that gives us our idea as to what's going on. The first guy is going to be the hypotenuse. Then you have a choice. You can put x, the square root of a squared is here. The square root of x squared is going to go either here or here. Traditionally you put it here. And why is that? Well, because this gives you that x divided by a is the sine of the angle. And what that then does is that whenever you do your substitution, dx is going to be a cosine of theta d theta. But if you were to put it down here, the only caveat or the issue you would have is that you would end up with a cosine substitution, and then the dx would be negative sine, and you'd just be throwing in an extra negative that we know sometimes causes trouble. So it's much better to just put it there, so we have our value of the sign, in this case our sign substitution, so that the derivative is positive. So it's silly. And in fact, one time in an exam when I was taking calculus, I actually did a cosine substitution because I never learned methods. I don't remember things. I just learned how to do it, where the logic lies. And I got marked off for not doing it. The sign substitution, the TA said it had to be a sine, not a cosine. Who does that? Well, I do. So anyways, but now I know better that to stick to the tradition. Now you can do cosine, but yeah. Anyways, regardless, you will solve it with a cosine substitution. That's all I want to say. Anyway, so here you see b would be this guy right here. So if you take a square root, this becomes the square root of a squared minus x squared, which is the one that we wanted. So this divided by a is going to be the cosine. So the cosine of the angle is going to be square root of a squared minus x squared divided by a. Just multiply times a on both sides, and then this gives you the substitution that you need. Let's look at it in the problem. So following these formulas here. So we have it here. A is going to be 3 for us because the square root of 9 is 3. And then our substitution, as we said, was going to be 3 sine of the angle. Dx is going to be 3 cosine of the angle, the differential of the angle. And now we said that the square root of 9 minus x squared was going to be 3 times the cosine as well. You see, I wrote that over here. Now that we can see from the triangle. If I would have drawn a triangle, that would have been quite nice, wouldn't it? Yeah, absolutely. Anyway, so let's draw the triangle now. Post or after the fact, not as nice. So the big guy, a, is square root of 9, which is 3. I put my x here, as I told you. And then here, this becomes the square root of 3 squared. So 9 minus x squared. So when I do adjacent over hypotenuse, it's going to give me the cosine. And I multiply times 3 on both sides. So with that, now I can plug it in. I can just get that this square root is just the 3 cosine. And as you noticed, I did not, I gotta make a point, I did not substitute just the x. I could have also gone ahead and grabbed my x and plug it in here, and my dx and put it in here, which is what I'm gonna do for the dx. And I would have then had 9 minus 9 of the sine squared. I would have had to use the fact that 1 minus sine squared is cosine squared, and then take the square root and get 3 cosine. It's a little bit easier to just do it from the triangle, in my opinion. Now, if you feel like the triangle is a bit challenging, you can always just get your substitution and substitute indirectly the x's and the dx, and then just go to war with it. I don't recommend it, as you can tell. I'm not very partial about that one. But, to each his own. Some people actually do prefer it that way. All right, so we'll do a lot of examples right now. I'm just trying to get you to see where the logic and how you draw your triangles. So this video is just how to draw the triangles. Once we learn to draw the triangles, then we're going to do a bunch of exercises. I'm going to put a lot of videos. I have old videos, but the quality is pretty bad. But we'll work as many as needed. All right, so now the last case, which is going to be where I have x as my hypotenuse. Why? Because it's the large guy, it's the one you're subtracting from, so it's the big guy. Now, your a you will not put here, because that would give you opposite over hypotenuse, which is a cosecant. Nobody likes a cosecant. That's all I have to say. I mean, it's true. So now this one is just the square root of x squared minus a squared. And so our substitution is going to be a x over a. Pay attention to this one. This hypotenuse over adjacent. So what is that? Well, it's the reciprocal of adjacent over hypotenuse. And adjacent over hypotenuse is cosine. The reciprocal of the cosine is the secant. You may want to rewind that one and watch it again. But that it gives you the secant. So a secant of theta. Then your dx from here is going to be a secant times tangent of theta. And now my square root, that's going to be square root of x squared minus a squared over a, is opposite over adjacent. That would be the tangent. Divided by a, I'm going to multiply the a on both sides, and I get a tangent of theta. All right, so that's how you determine your substitutions. Let's put it in the last triangle, and let's wrap the video up there. All right, so here a is going to be equal to 1. x we said was going to be our secant, 1 times secant. Dx is secant times tangent. So I can substitute that in. Now I have this one, the square root of x squared minus 1. If I draw the triangle, I'm learning my lesson. Here we go. I'll draw it real quick. Oh, there, I did it. All right, so what I have here is x, and then I put the 1 here. This is the square root of x squared minus 1. And then if I do x squared minus 1 divided by 1, opposite of adjacent, oh, I have it written there. Opposite of our adjacent is the tangent. So I can plug in this. However, careful, I still need, I'm going to have to throw in a cube. Why? Because I have the 3/2, so it's going to become a cube. Now, normally you wouldn't do that. I mean, I'm just doing that because well, that's what the problem is asking for. So then all I have to do is plug in things. So I think I'm going to write it here. The dx is going to be secant tangent d theta. Ooh, d theta. A little too excited about, like, okay, it was not that big of a deal. Well, it warranted a ooh. Anyways, divided by tangent cubed. Here what I'm gonna do is I'm probably gonna cancel a tangent. I'm gonna have tangent secant over tangent squared. That one probably better to secant over tangent squared. That's probably one of those that you turn into sines and cosines, and you end up with a sine square over cosine. I'm almost wanting to solve this one in the next video. I think we're gonna solve that one in the next video. Anyways, we'll wrap it up here. This is your substitution. The only thing you can do right now is cancel, and we'll take a look at that one. That may be where we start the next video. All right, thank you for watching, and let's stop right here.